Hi. Before I go anywhere else, I want to apologize in advance. I'm in a room right now where there's some construction happening in on the second floor above me, so you may hear some construction noise during the recording. Not much I can do about it, so sorry about that. In fact, there it is. Yep, apparently you can hear that. Well, hopefully it won't be too distracting. All right, so in the previous recording, I introduced a couple of new concepts regarding energy. First of all, I mentioned a new kind of energy that I call thermal energy, which I haven't described in any detail yet, except to say that it is somehow connected to some common concepts of heat and temperature and things getting warmer and stuff like that. The problem is, of course, I have not yet defined what heat actually means. I have not, in fact, defined temperature. And you know how we physics types are. We have to define everything so that we all agree on what we're talking about. And for that matter, so that I can eventually put equations to all these things. So we have to move past our common feeling for what heat is and what temperature is and what hot and cold mean and expand to more precise definitions, or completely precise. A particular concept of thermal energy, which, well, first of all, the significance of this question mark here is I don't really know what it is yet, or at least I haven't told you what it is yet, and then I haven't told you what these other things are. The symbol, by the way, for thermal energy, you remember from the previous lecture, was E sub TH for thermal. Okay, and I pointed out that the new thing about thermal energy that makes it very different from kinetic or potential energy is that it, although it's easy to transform kinetic and potential energy into thermal energy, the reverse is not true. It's difficult to convert thermal energy into kinetic or potential. It can be done, certainly, and we do it all the time, but the conversion process is not 100% and usually not even close to 100%. And so 100 joules of thermal energy cannot be converted into 100 joules of kinetic energy. There's always less kinetic energy or potential energy than that. So the significance here, as I write here, is that evidently, since energy is not lost, because part of the whole point of thermal energy is to actually save conservation of energy, but the force that caused the transformation from kinetic and potential into thermal energy is going to be a non-conservative force. And this is simply because of how conservative force is defined, that you get back on the way out what you lost on the, if you make a round trip, where the energy that you lost on the way out, you get back again on the return trip. That's a conservative force. The energy that you lose on the way out, you gain that energy back again, perhaps in a different form on the return trip. But that's not true with thermal energy. If you lose energy to thermal energy on the way out, you don't get it back again on the return trip. So it's lost to your system. Well, it may be lost to your system, but anyway, you can't convert it easily back into potential or kinetic energy, which then, by the way, led me to the term I just used, your system here. So the system is, as it has always been, the part of the universe that you're currently asking questions about. And in our current topic here, we want to classify systems by how they interact with the rest of the universe. So we have open, closed, and isolated. So open, mass and energy of your system can change, and so we have to deal with that. A closed system is the mass will remain constant, but energy can flow into or out of the system through the system boundaries as it happens. And then isolated, meaning that neither of those things can change. So this is just terminology, so we can, again, just defining our terms so we can talk to each other. And then finally, the related concept of surroundings. Basically, the surroundings is whatever is left when apart from your system, basically the rest of the universe. Okay, everything outside of your system. Okay, so to take the next step, I want to, and my next step is what is heat, what is temperature, okay? And to explain and define those things, I need to talk about what thermal energy is, first of all. Because I've just said, oh, let's call this new thing thermal energy, and we have this vague idea that it has something to do with things getting hotter or colder. What's going on with that, okay? So to so my task now is to define thermal energy, explain what it is and how it comes about physically. And then as a consequence of that, I'll be able to define heat and I'll be able to define temperature. So let's go ahead and start. Move over to the next board over here. So to explain all of that, so I need to start out examining the question of what is a system and what's going on. And I just happen to have a nice example here, my grande drip here. And, oh, well, what's in here? Well, more or less hot coffee. It's not as hot as I'd like anymore. Why? Because it lost energy to its surroundings. Okay, let's back up. First of all, my system. What is my system? My system, in this case, I'm going to just choose it, and you're typically allowed to choose your system. You choose your system, as always, based on what questions you're trying to ask and answer. Okay. So I think I'm going to ask questions about how hot is my coffee right now? How rapidly did it cool down? How much energy or something do I have to do to heat it up to the temperature that I want to drink it at? What do all these words mean? Okay. Again, that's my goal is to answer all those things. And so to start with, let's choose my system. My system is going to be the coffee, the liquid inside this cup. That means, by the way, that the surroundings is, of course, all the air in the room and everything else, okay? And I mentioned in the previous video that technically, I think the example I used was the planet Jupiter is part of my surroundings, but it's not really affecting my coffee, so I'm not worried about Jupiter. No, my surroundings as a functional matter is going to be the air in the immediate vicinity of my cup. And then another piece of terminology for you here, the paper here is the boundary between my system and the surroundings. So there's a third term for you here, the boundary. Whatever it is the physical barrier between your surroundings and your system. So I suppose I should put that in over here. Okay. So in my example here, then, as I said, my coffee, the actual liquid, is my system. The air is the surroundings, and the paper cup is my boundary. Let's go back to the other board now. Hope that doesn't make you dizzy, all that moving around. Okay, so let's take a look at my cup of coffee here. Okay, and I've got a lid on it here. I'm not going to draw the lid right now. Well, maybe I will. I'm going to try my drawing skills to their maximum here. Perfect. It's just like a Starbucks coffee lid, don't you think? I think so. Okay, and then my coffee is in here. Okay, well, I'm trying this. Well, okay, so my cup is partially full, and of course there's air up above it, and then there's air surrounding. So my coffee, there's my system, the air around surrounding the paper cup and the lid, my boundary. I guess this should be circular. Why do I care? I don't know. Yeah, it's more realistic. And there's the hole I drank through. Now I'm overdoing it. Okay, so what do we have? Well, this is fine as far as it goes, but for my purposes, this drawing is insufficiently detailed. So let's start here. And first of all, I'm going to erase the coffee and replace it with a different representation, which is, of course, as you know, coffee is basically two things. It's mostly water with a little bit of coffee. In this case, it was espresso. Yeah? Well, no, I guess it was a drip, so whatever. Anyway, whatever coffee is, it's some kind of molecule, and it is dissolved in the water. So primarily, the contents of my coffee cup is water with a little bit of other brown liquid dissolved in it. Okay, so for a first approximation, let's just think about it. Think of it as water, so I don't get excessively complicated. Well, water, you know what water is. It's actually a bunch of water molecules, H2O molecules, and then, like I said, a bunch of other things which I will refer to once in a while. H2O molecules, and they are, there's quadrillions upon quadrillions upon quadrillions of water molecules in just an ordinary cup of coffee, right? And so if I wanted to, I could draw a whole bunch of little H2O, and then H2O, and H2O, and a couple more, I guess, H2O, and so on. I could just draw a whole bunch of these, and there's, of course, I'd have to really represent it. I'd have to draw them really, really tiny, and again, quadrillions upon quadrillions, which I'm not going to try to do. Instead, I am going to simplify this down and represent each water molecule, and in fact, every other kind of molecule in here as well. I'm just going to represent them as dots. Okay, so all these little dots here are meant to represent primarily water molecules, a few coffee molecules. I added some sugar and some milk because that's how I like my coffee. So there's other things mixed in there as well. Okay, so there's that. The point that I want to make here is that in order to understand the various concepts that I'm starting to introduce, the first thing we have to realize is that this stuff that we look at macroscopically, you know, with just our eyes, and we see it as a continuous liquid, is of course made up of a vast number of very tiny but individualized particles, which in this case those particles are water molecules primarily. That's the first thing. And similar statements are true, by the way, about the air in the surroundings of our cup. The air in which you are currently standing and the air you are currently inhaling and exhaling is made up of molecules of various kinds. 78% of what you're breathing right now, assuming you're watching this on the surface of the Earth, about 78% of the molecules that you are currently inhaling are simply nitrogen molecules, N2. The remaining of the remainder, 21% are oxygen molecules, O2, and the remaining 1 or 2%, whatever it is, are admixtures of other things, water, vapor, and carbon dioxide, and carbon monoxide, and various pollutants of different kinds, and so on. But again, the key idea is that I need for my purposes is that the air is not a continuous unbroken gas, but is made up of particles, mostly nitrogen, a little bit of the other things. And these particles completely surround our system, separated from our system by the boundary, the paper cup. So we have the surroundings, we have the boundary, and we have the system. All right, so far so good. The next piece of information that we need in order to understand temperature, heat, and thermal energy is we have a physical and physiological human response that allows us to identify that this thing is hotter than that thing. We just touch it and we can just feel it, okay? So what's going on there? Why is one thing hotter than another, and do I have a technical definition for the word hotter? The answer to the second question is yes. As far as the first question, it turns out that, and this was discovered after a lot of investigation, but here's the answer. The difference between two things, one hotter than the other thing, even if the two things are otherwise identical, right, is, so take two pots, two aluminum pots, get one really hot and the other one leave it at room temperature. What's the difference between them? They don't look any different, and that's why you can burn your hand, because they don't look different to your eyes, but you grab a hold of one that's way too hot, and of course you can get a bad burn. But there's nothing visibly different. What's going on? The answer is that the particles, and now I'm going to switch back to my coffee, the particles that make up my coffee here, the hotter the coffee is, what happens is these particles are in motion. Okay? They are literally moving, velocities. And since they are moving, they not only have velocities, but they have mass as well. And so in terms of energetics, what we say is that the coffee, when the hotter it is, the faster these particles are moving, or in other words, the hotter the coffee is, the more kinetic energy each of the molecules, each of the water molecules, each of the coffee molecules, the more kinetic energy each particle has. So in short, the temperature or the hotness, if you will, how hot or cold something is a direct reflection of how much kinetic energy each of the particles of your system has, how fast each particle is moving. But kinetic energy is better because the mass matters also. I said a little bit ago that I was going to just treat this as essentially a collection of water molecules, but that's not strictly true, otherwise I wouldn't be drinking it. No, there's also coffee molecules and milk molecules and sucrose molecules all mixed in here. All of those molecules have different masses. And therefore, even if they're moving at the same velocity as the water molecules, of course, they have more kinetic energy. So the mass matters also. So in short then, the thermal energy, and this is where I'm going now, is caused by, is due to, and frankly is a direct measure of the kinetic energy of the particles that make up the system. Okay, and to the extent that you have different kinds of particles, so presumptively with different masses is the usual distinction, you have to worry about the kinetic energy of different particles due to their different masses as well as to their differing velocities. Okay, so in short, the faster these particles are moving, the more thermal energy our system has. And we detect that again, a physiological response to this higher temperature is that it just feels hot to us. It's something, one thing feels hotter than another thing due to the internal kinetic, individual kinetic energies of the constituent particles. You'll notice, by the way, I left a gap here because there's a word that's missing. As the particles move about, they are actually, of course, much closer to each other than I've drawn here. They're continuously colliding with one another. And so, of course, when they collide, their kinetic energy tends to, will inevitably change. And so we're talking about 10 to the 23rd, many times 10 to the 23rd number of particles here. It's a hopeless task to even imagine keeping track of the kinetic energy of each particle one at a time. We couldn't possibly do it. It's physically impossible. So we don't try. We talk about the average kinetic energy of all the particles. Now, there is a way to calculate this average kinetic energy. We are not going to worry about that, at least not right now. We'll just sort of assume that we can somehow calculate the average. And it is this average kinetic energy then that we think of as the thermal energy, or the so-called internal energy. That's another name for it. The internal energy here is a direct indicator of, and it's caused by, the average kinetic energy of all these particles. You average over all the particles. Okay, so there's that. And the next question is, okay, so we have these particles in here. What about the air molecules outside? Isn't that also true of them? And what role does the boundary play? You can probably guess, but so go ahead and guess while you fire up the next lecture.